The rest of the reactions that we have in this chapter are ones that you've seen before. We've seen that carboxylic acids will react with bases. We've also seen that we can reduce acids to alcohols with lithium aluminum hydride. Just remember that lithium aluminum hydride is aggressive and reduces everything: aldehydes, ketones, esters, nitro groups, and cyanide or nitrile groups. So keep that in mind when you're using lithium aluminum hydride. In the reactions with bases, of course, acids are going to react with bases, and we've seen this before. Here we have a carboxylic acid will react with sodium hydroxide to make the salt. This is what gives acids water solubility. We can get even fatty acids, long chain carboxylic acids, to be suspendable in water by reacting them with sodium hydroxide and making the carboxylic acid end very hydrophilic. But organic acids will react with organic bases too. We haven't really seen this reaction much. If we have, we haven't emphasized it much so far. But realize amines are bases and carboxylic acids are acids, so they react together. When they react, all you have is proton transfer, and you form a salt. It's just not like the inorganic salt up here. You don't have a metal in there. What you have instead is the ammonium carrying, or the amine carrying the positive portion of the ion, and the carboxylic acid carrying the negative portion. But these are water soluble just as the carboxylic acid salts with metals are soluble. And it is this reaction right here that makes amino acids be so water soluble and also exist as a salt, not as a neutral compound, or not as an uncharged compound. Okay, if we look at carboxylic acids, we can reduce them with lithium aluminum hydride, but realize we'll also reduce nitro groups. There are ways of reducing the carboxylic acid to an alcohol without the nitro group being reduced. You can use borane, actually, what we use to take an alkene to an alcohol. We can use borane to reduce a carboxylic acid to an alcohol, but we're not going to be covering that in this material. If we use lithium aluminum hydride, we will reduce carbonyls, and so here we have the carboxylic acid is being reduced to an alcohol, but so is the aldehyde. Now we can, using sodium borohydride, a weaker reducing agent, leave the carboxylic acid intact and just reduce the alcohol. And if we were going to be covering it, borane would reduce the carboxylic acid and not reduce the aldehyde. But again, we're not going to be covering borane reduction. But keep this in mind, the selectivity difference between lithium aluminum hydride and sodium borohydride. So, knowing what you know now, how would you make 3-phenyl 1-propanol from styrene, or this alcohol from 2-propenoic acid? Go ahead and pause the lecture and then restart it after you've... So how would you make 3-phenyl 1-propanol from styrene and this alcohol from 2-propenoic acid? Let's look at it. 3-phenyl 1-propanol from styrene. First, let's put styrene down, and then let's put the 3-phenyl 1-propanol. And if you look at that, you can kind of see where your carbons are. These two carbons have to be these two carbons. You can see you have to add another carbon in order to make this molecule. Have we learned how to add a carbon? Well, either through carboxylation or with a nitrile. So let's go ahead and see what intermediate we are going to have. Both the nitrile and the carboxylate from the Grignard reagent have this as your product before you would have reduction to the alcohol group. So I can go back from here to here. Then how do I get from here to there? Well, I'm going to have to somehow change this to have a leaving group or something that I can have with a Grignard reagent. So I can put a halide on. Now you notice this is anti-Markovnikov addition of the halide. Well, let's look at what conditions can we use to go from styrene to anti-Markovnikov addition of bromine. Notice it would be hydrobromic acid added across this double bond. Well, one thing we haven't discussed much in this course is that if you use hydrobromic acid and you have free radicals in there, you get anti-Markovnikov addition of the bromine. But if you couldn't recall that, what could you do? You could use borane and, oh, we're missing a 2 right here for the peroxide. But use borane followed by hydrogen peroxide and hydroxide. And then when you're through with that, you could tosylate it and use sodium bromide to do an SN2. So either hydrobromic acid and free radicals or the more lengthy step. Well, to go from the bromide to the carboxylic acid group, you could do an SN2 with sodium cyanide, or we can use a Grignard reagent and carboxylate it. Either would work fine. Once we have the carboxylic acid, what can we do? We can use lithium aluminum hydride to reduce it down to the alcohol. So how do we make this alcohol from 2-propenoic acid? Well, let's write down the 2-propenoic acid and look at the alcohol and how we might be able to see the carbons in here. Notice we have the alcohol group. That must be right here, this carbon, the carboxylic acid group here. So where would these 2 carbons be? They would be right there. And doesn't that make you start thinking about a Diels-Alder? This has got to come from a Diels-Alder adduct where this used to be from the diene. So we could react this propenoic acid with a diene, this diene, and we would end up getting this cyclohexene, and that cyclohexene carboxylic acid could then be reduced with lithium aluminum hydride.